Yeah, so thanks for being here and to listen to me. And today I will present my currently work. It's about the platform for issuing and verifying documents in the public blockchain. So this is the outline for today. So I will start with an introduction of myself and the research center where I'm coming from. And then I will motivate the topic, followed with related work. Then I will introduce two preliminaries. So we'll shortly go for blockchains, so what we expect from a blockchain, and for a key derivative function which we use to create public-private keys in our platform. And then I will talk about the platform itself, and finally I will conclude with a summary and the outlook. Okay, let's start with introduction. So my name is Clemens Brunner. I'm doing a research visit until the 24th of May. So I'm here until the next week. And my interest is in decentralized trust management systems, or also decentralized PKIs, authentication methods, and privacy enhancing technologies. I did my master's in computer science at the University in Innsbruck. My thesis was called Ethereum, and SPROOF is now the successor of Ethereum, and my supervisor was Rainer Böhme. Currently, I'm a PhD student at the University of Salzburg. My topic of the thesis is decentralized trust management systems for privacy-preserving authentication in the smart grid, and my supervisor is Dominik Engel. And I also try to come up with a startup. So we are now in the starting phase of the startup. And yeah, it's actually a decentralized middleware and the API for registering data on the blockchain. So it's the practical side what I present today. And so my main job is I'm a researcher at the Center for Secure Energy Informatics of the University of Applied Sciences. So there's a difference in Austria of applied sciences and a university. And yeah, we have the research center. I'm working here, and I'm doing my PhD at the University of Salzburg. And the center where I'm working was founded 2013, and it's based in Salzburg, in Austria. We are currently 18 researchers. Yeah, this is our website, so you can look at it if you want to see our full list of papers. That's the topics we are working on, and we also work with local utility providers in Salzburg and in Austria, and also bigger companies like Siemens or Bosch. So it's a practical research center. Yeah, and if you want to visit Salzburg or our research center, yeah, feel free to contact me. I think we can arrange something. Okay, so why we created that platform for issuing and verifying documents. But before I told you that, I just want to bring a brief overview what it is about. So I have here the term documents, and to clarify the term, I have a few examples. A document in our platform is, for example, an educational certificate, attendance confirmation, a certificate of employment, or actually basically just data or identification documents. Each document has an issuer, and the issuer should be or is publicly verifiable. And a document can have a receiver, and the receivers are constructed in a privacy-friendly way. How we construct them, I will explain you later. And the third actor is the verifier. And the verifier should be able to verify a receiver of a document, but only with the consent of the receiver. And the verifier should be able to verify the document itself and the issuer without contacting the issuer, for example. Yeah, why we do that? So yeah, there is fake information, and there is a study on Carrier Builder. It's quite old, but it was there. So 58% of the employers have caught a lie on a resume, and yeah, that's one motivation for us. Another motivation is that consider if you got your printed diploma, you lose it, you need to get a copy maybe, then you need to go to the institution and ask for a copy. But what happens if the institution is closed, corrupt, or even destroyed during a war? You have, it's very hard to get a copy. And to verify such printed documents is also time intensive and actually costs money. And another motivation for us is also the central trusted third party. So we try to avoid the central trusted third party in our platform. Maybe you think, why you just use, or why do it not with digital signatures and a PKI? So we do that. We use digital signatures and a PKI, but there is also a problem with the PKIs, we know, because we need to trust in a third party to, for the timestamping and ordering the documents, and also for managing a distribution of revocation lists. So consider if we have a CI which issues a certificate, it puts a signature on it, but to revoke that certificate, actually, we need a place anywhere where we store the information or we can look it up. And the current methods do not provide, we need to trust in the CI that the revocation list, for example, is complete and the information is available and not modified. And that's one main objective of SPROOF, that we want to make central trusted third parties for issuing and verifying documents obsolete. So we want to create a platform which does not depend on trusted third parties. Okay, before I talk about the related work, I define some properties to evaluate them. So the first is decentralization. So the verification of documents should be possible without a trusted third party. It should be permissionless, so we do not want to apply any access restrictions, who is allowed to issue documents in the platform and who not. And also, there is the property like if there is a built-in mechanism to verify the identity of issuers, or it's just relying on public keys, and we say, verify the public key, not in the platform, so maybe in other platforms. And completeness feature, it's we say it's if there is a mechanism to group related documents and verify that such group is complete or not, then we say that have this completeness feature. But I will explain it in a more detail later on. And here, that's just a selection of the related work, because there are lots of startups and new projects which trying to solve this issue. But here we have the University of Nicosia, who was actually the first who issued a document or a certificate on the public blockchain. Then we have a very famous project called BlockCert from MIT, and also the lifelong learning passport. And we see that the completeness feature is pretty unique to SPROOF. And also the integrated issue verification mechanism is not always there. And the lifelong learning passport, for example, is not permissionless because they decide who is allowed to use their platform. Okay, now I will explain you two preliminaries. So first I will talk very short about blockchains, and the second part is about the key derivative function. So what we expect from a blockchain is, or how we describe a blockchain is that a blockchain is a globally consistent, decentralized, transparent, and authenticated database. The entries are chronologically ordered, it's tamper-proof, and the users are represented by public-private key pairs. A transaction is basically a write request to the blockchain, which is signed, and the miners will write it then to the blockchain. And we all know that storage is very limited on blockchains and very expensive. So therefore, we defined the term public storage, where we just append a hash reference of data in a transaction, and actually data is then stored in a distributed hash table, for example, IPFS. yeah, so the IPFS hash is a cryptographic secure, they use a cryptographic secure hash function to address the data, and we embed that hash in a transaction. Okay, so the key management, so we use hierarchical deterministic wallets, or HD wallets for short. With its hierarchical construction, so it is possible to generate child key pairs out of a master key pair, and the child key pairs can then be again used as master key pairs. With that construction, it's basically possible to build an infinite tree of public-private key pairs. And here we can see an example. So we have a seed, construct a master key pair, and then we can create the children and so on. And there is one interesting thing about those wallets, and it's called the master public key property. Maybe you knew it already, but I will just explain it again. So the master public key property is that it is possible to generate the child public key corresponding to a child private key given only the master public key and an index I without knowing the master private key. So for short, it means that if I give you some public key, you can construct the subtrees for all public keys, and you do not get any knowledge about the private keys attached to it. And that actually, we use that tree to accomplish the completeness feature. Okay, so let's talk about the platform itself. So that's a very simplified overview. So we have here an issuer, the receiver, a verifier, and here we have the middleware, blockchain application, or backend, or node. And we have here 3 modules. And we have here the issuer, and the issuer adds events to the public storage module. And that events can be, for example, grant a certificate, revoke a certificate, and stuff like that. And such a list is then stored in the DHT and logged in the blockchain. And then the event state machine reads the data out of the blockchain in a chronologically order, fetches the raw data from the DHT, and parse everything and validates all the events. And actually this basically works on top of any blockchain, so we can just put it on the blockchain. And then we calculate a globally consistent state and we store it in a local database, and we then just use the database for API queries. So then here it's actually just the server client architecture. But the data is stored publicly. So let's go a little bit deeper to this part. So I said something about events. So events are the way to trigger a state transition, and only issuers are able to add events. And we combine multiple events into a single transaction, which is signed by the issuer. So we have here a list of events, for example, issue first certificate, second, and so on. And we create a hash reference, or we store this file in IPFS. Then we get the hash reference, and this hash reference is then sealed in a blockchain. Okay, so let's take a look at the issuer construction. So how it's possible to be an issuer on the platform. So the first step for an issuer is to create a public-private key pair. And then the issuer has the possibility to add an identity claim event. And it's just a claim of the identity. So everybody can claim, for example, I can claim that I'm the KU Leuven, for example. And nobody has a proof for it. And therefore, we provide identity evidence events which should bootstrap trust. So for example, you can add in those events your website, and on your website you should put the signature over your public key. Or for example, you can add here a post of your social media account, just post your public key, and provide the ID of the post, and then we can match the connection. Or also just attach standard X509 certificates. But as I said before, we do not depend on central trusted third parties, and that's actually central trusted third parties. And therefore, we introduce the confirm event, so the issuers can build kind of web of trust where each issuer can confirm other issuers, and then we can create a confirmation network of universities, for example, or other companies. Okay, with these 4 steps basically, or after that, an issuer is able to register a document with this event, and a registration looks basically like this. So we have the issuer, it's the public key of the issuer, we have a validity period, and then we have 3 ways to append data to that event. Like the first is to just append the JSON object directly. We can also append a DHT location hash, for example IPFS, or also a hash of data which is stored privately. And we can also add dependencies to other registration events. And finally, we also can append a list of receivers to those registration. Another question is how we represent the receiver on a document. And that I will explain to you now. So we're now here. So the receivers again are represented by public-private key pairs. But if you will use the same key pair for all documents, then all documents would be linked together because it's public information. And if you have one key, you can look up for all other documents. And therefore, the receiver only has the possibility to share all documents. And therefore, we use a new pseudonym for each document. And we do that with HD wallets. And with that, we can create verifiable groups of related documents with the master public key property. So here you can see an example of, so let's say that's my, it's my master key. So I share this pseudonym with a university or with an issuer and only the public key. And then the issuer is able to create this structure of the groups and issue documents for me. And let's say this is a course, or this is my bachelor studies, and these are several courses. And then I want maybe 2 of them are very well graded. So I have here an A and maybe I have here an B. I do not want to share the B with a verifier. And I share these 2 documents and say, hey, look, I only have A's. And if I do that case, the verifier can conclude or can say, hey, you sent me 2 pseudonyms, but you have the possibility to just send me 1 if you go 1 step higher in the tree. Why do you do that? So then the verifier can say, maybe he hides some information. And on the other hand, the receiver can just share a pseudonym at this level or at this level. And so just sharing a single pseudonym means he shares a complete group. And if he shares 2 pseudonyms, which indicate that there is some information missing. And so the completeness, a pseudonym, when you share a pseudonym at the high level of the tree, it increases the completeness of the information. And if you go down, you increases your privacy because you also can share just a single document. But pseudonyms they do not contain any information about the real identity of the receiver. And we said we need a link to the real identity because receivers can collaborate, for example, and share the private keys. And therefore, we attach the real identity to a document. And here we constructed a hash tree. So this should represent the hash of the concatenation of those values. And so if we look at that tree, we have here again a validity period, and we have a hash of a list of attributes. Here we have the attributes, and then the receiver for example, if I want to attach here my date of birth or my name, I can just add here, the name of the attribute is date of birth, the value is my date of birth, and then I attach a salt value to it, and then I can create this hash reference. And with this construction, a receiver has the possibility to share multiple, or the values which represents the hash reference of attribute 1, for example, without sharing the other ones. So he can share selectively some attributes which he wants or not. And actually, the representation then on the document for a receiver is a new public key, px, from the pseudonym tree, and the root value of such attribute tree. Okay, how does the verification look like? So first we need to get the global data set of SPROOF, and we do that to iterate over all transactions in the blockchain once, collect each events and apply them in a state machine and create the local database. And if a new transaction will be attached to the blockchain, it will trigger an update on the local database. And then this database is used to query the state. For example, we can look at the state of the document, if it's revoked or not, or also the state of the issuers, for example, a confirmation network, and so on. So to verify actually a receiver, we have two approaches. We have the pseudonymous approach, where the receiver just creates a signature over his pseudonym for a verifier. And also the receiver has the possibility to reveal some attributes and share a list of selected attributes. To verify an issuer, we have the identity claim event in combination with the evidence event, or we can also look at the confirmation network from the receiver, the issuer. Okay, so here's a small summary. So I presented you today a platform for issuing and verifying documents in a public blockchain. We have a globally consistent state. We have a privacy-friendly representation for the receivers. The issuer is publicly verifiable. We have a minimal usage of the blockchain, so it will be cheap. And we can verify the completeness of a group of documents, and we can also share selected documents. We do not need any trusted platform operator. And the outlook is I will work on the implementation. So basically the proof of concept is done, and there is also a prototype, and I want to present this. Maybe we can use zero knowledge proofs for verifying specific attributes, for example, like the date of birth, to show that you're older than a specific age instead of sharing your real date of birth. And I also want to evaluate the usability of blockchain-based applications and also SPROOF. We also have a website, so if you're interested you can go look at it. Thanks for your attention, and feel free to ask questions.